Hello everyone and welcome back to the Regents Chemistry Review Series. In this video, we're going to talk about equilibrium. So let's start with the definition of equilibrium. So equilibrium is normally represented by a reversible arrow or by a double arrow, which indicates that whatever system or reaction we are looking at is reversible, meaning that the rate of the forward reaction is equal to the rate of the reverse reaction. So if you look at this diagram on the side, we are observing that the rates are equal when the equilibrium is achieved, which is along this line over here. So after the equilibrium is reached, we see that both of them are occurring at the same rate. However, the thing to keep in mind about equilibrium is that the rate, meaning the speed of the reactions, is the same, but that does not necessarily mean that the concentration of our reactants and products is the same. The concentrations are constant, which means they don't change anymore. They remain constant, but they are not equal. So as you can see in this picture over here, we have less concentration for N2O4 and more concentration for NO2, but they're just staying constant, and the conversion between both of them is the same. So if we try to write an equation for this reaction over here, we are going to figure out, we have the double arrow in between, and we want to figure out which one out of these two gases is our reactant and which one is the product. So is NO2 the reactant or is N2O4 the reactant? So we notice that NO2 is starting with a 0, and N2O4 is starting with some concentration. So whatever is starting with a 0 tells us that this was not present at the beginning of the reaction. So that means it's most likely our product, because we always start with the forward reaction, right? So if at the beginning of the reaction we did not have this substance, that means this was our product for the forward reaction. And then N2O4 had some concentration at the beginning of the reaction, so that was what we started with. So we write that on the reactant side. So we can have equilibrium occur in different circumstances. We can either have phase equilibrium, so if any type of phase change is occurring in a closed system, for example, let's say you have a closed bottle which is sitting at like a very high temperature, the water in that bottle is going to evaporate because of the high temperature, but then because it's a closed system, it's also going to condense eventually. So when the rate of condensation and evaporation is equal in that closed system, we say that we have a phase equilibrium. We can also have the solution equilibrium that we talked about in the solutions unit. So this is when we have a saturated solution, because at that point the rate of dissociation is equal to the rate of crystallization. And then finally, we can also have chemical equilibrium, which is what occurs in chemical reactions. So this is when the rate of forward reaction is equal to the rate of reverse reaction. And we can actually visualize the equilibrium in chemical reactions, and this is when any type of evidence for chemical reactions is staying constant. So if we were observing a color change, if the color stops changing, then that represents that we have already reached equilibrium. So we before we talk about how is equilibrium, or how can equilibrium be impacted in chemical system, let's first talk about this idea of rate of the reaction or the speed of the reaction. So the speed of the reaction depends on the collision theory, which states that for any chemical reaction to occur, the particles of the reactants have to collide with each other at very specific orientation, and they need to have a certain amount of energy. So if they are not colliding with each other with proper orientation or with proper amount of energy, then we do not have effective collisions, and so the reaction does not occur. So we need the proper orientation and sufficient energy for effective collisions. So If we want to speed up the reaction or increase the rate of the reaction, we want to have as many effective collisions as possible. So there are a few factors that can impact the number of effective collisions. The first thing is the type or nature of the substance that we are looking at. So ionic versus covalent. If you're looking at an ionic compound, they can dissociate into ions. And so there are going to be, when there's more particles in our solution or whatever reaction that we are looking at, then there are more chances of effective collisions. Compared to covalent compounds which do not dissociate. Aqueous versus solid. If we have an aqueous solution, once again, the whatever substance we are dissolving is most likely going to dissociate into ions, and those substances are going to move around freely. There's more mobility, and as they are moving more, they're also going to be colliding more. So there are more chances of effective collisions compared to in the solid phase when there's no mobility. When we increase the temperature, the particles move very, very fast because we are also increasing the kinetic energy. So as they move fast, once again, we are going to have a higher chance that they are going to collide with each other at with certain amount of energy and add proper orientation. And if we add a catalyst to the system, that is going to decrease the activation energy. So that just in general speeds up the reaction, because that means the sufficient amount of energy that we need for the reaction will get that faster. And then for if we increase the surface area, then that is also going to increase the chances of effective collisions, because normally we increase the surface area by decreasing the particle size. So think about if you have a solid substance, maybe a chalk in the solid form, right? So you take chalk in the solid form and you put that in an acid and you try to dissolve it. And you compare that to the powdered form of chalk and you put that in the acid and you try to dissolve it, the powdered form is going to dissolve much quicker, and that's because the particles are separated from each other, so there's more interactions between the particles and the solution. So the more interactions there are, the more collisions there are going to be, compared to in the solid form of the chalk, only the particles at the surface are interacting with your solution or with the acid. Okay, so then the concentration, if we increase the concentration, once again we have more particles, so we are going to have more chances of effective collisions. And finally, if we increase the pressure, this is something that is only going to have an impact on gases, because remember, solids and liquids are not compressible, so increasing the pressure or decreasing the pressure would have no impact on their structure or their particle arrangement. However, in case of gases, if we increase the temperature, that is going to bring the particles closer together. So now that there's less space, we can hope that there's going to be more collisions. So increasing the pressure can work in favor of the gases and make them react faster. So Le Chatelier's principle is a very important concept in equilibrium, because this is the principle that states that if we have any reaction or any system at equilibrium and we stress the system by changing something, so what are the things that we can change? We can start heating up the reaction, or we can add more reactants or products, or we can maybe change the pressure or anything of that sort. So if we are looking at a reaction that has already established equilibrium, but then we stress the system by changing any of the factors, then the system is going to respond to that stress. It will try to relieve that stress or get rid of the stress by shifting in the appropriate direction. So it will either shift to the right, meaning it's going to increase the rate of the forward reaction, or it's going to shift to the left, meaning it's going to increase the rate of the reverse reaction. So here's an example reaction at equilibrium that we can use to guide our conversation. So let's first talk about a change in the concentration. What if we go ahead and increase the concentration of nitrogen? By the way, this symbol that you use, remember the brackets, we were using this to represent concentration. So the N2 written within this bracket represents the concentration of nitrogen. Okay, so if we increase the concentration of nitrogen, now we are going to have more reactants. So there's more substances on this side. What this is going to do is it's going to increase the amount of collisions on the reactant side. So there's hopefully going to be more effective collisions on the reactant side between N2 and H2. So because there's more effective collisions on this side, the reaction is going to shift to the right, because now that these two things are colliding more, they are going to react more and they're going to produce more of the product. So in class, we did the little hand model thing. So we said that let's say this is your, oh wow. So this is your right hand, this is your left hand. I do not want to try making the hands, even though I can, but like that's gonna take some time. So okay, so your left hand represents the reactants and this one represents the products. So we were practicing which side goes up, because in chemistry things go from higher to lower. So we said that if the reactant side is going up, then the reaction is going to shift from high to low. So that means it's going to go to the right. So what if we decrease the concentration of nitrogen? So now we are going to, let me change the color. So now we are going to decrease the concentration of nitrogen. So once again, this is your reactants and this is your products. So if we decrease the concentration of the reactants, once again we are going to go from high to low. So now the reaction is going to shift to the left, because there's going to be less effective collisions between N2 and H2, and there's going to be more effective collisions between the ammonia molecules on the product side. So we'll have more ammonia converting or dissociating into nitrogen and hydrogen gas. Okay, so there's something called the common ion effect, which basically has to do with adding something in our solution that is only going to increase the concentration of a specific ion in our solution. For example, we are looking at this reaction right here where lithium sulfate is breaking down into lithium and sulfate. So what would happen if we go ahead and add H2SO4, which is sulfuric acid? Now here's the thing, your sulfuric acid, when it goes in the solution, is going to break down into hydrogen and sulfate. There's no hydrogen in our initial reaction. So what this is going to do after we add sulfuric acid is it's only going to increase the concentration of the sulfate. Yes, we still have that hydrogen in our solution, but that is not going to impact this reaction. Okay, so it's only going to increase the concentration of the sulfate ion. So now, because if we do once again the reactants and the product side, because our product side is higher, we are going to have more collisions between lithium and sulfate ions. So that means the reaction is going to shift to the left. Okay, so this is how the common ion effect works. You just have to see which ion is going to be impacted. So that is going to make that side kind of higher in concentration. There's going to be more collisions on that side and the reaction shifts to the opposite side. Okay, so let's look at continue with Le Chatelier's principle, and let's focus on temperature for now. What if we increase the temperature? So remember that increasing temperature is also going to increase the kinetic energy, which means particles are going to start moving very, very fast. And in this case, we notice that we have the energy written on the product side. So an easier way to kind of work with this problem is once again use our hand model thing and say that this is our reactant, this is our product. And if we have energy on the reactant side and if we are increasing the temperature, we are technically adding more energy to the product side. So the reaction is going to go to the left. Meaning it's going to increase the rate of the reverse reaction. So this is a very easier way to come up with the correct answer. So if we decrease the temperature, it's going to be the other way. So here's your reactants, here's your products. We are decreasing the heat energy. That means we have less energy on the product side now. So now it's going to go to the right, and we are increasing the rate of the forward reaction. But it's also very important to understand a very, very key concept here. And that key concept is when we are adding the heat, it is going to increase the kinetic energy of all the particles, whether they are on the reactant side or they are on the product side. However, we have to keep in mind what type of reaction is the forward reaction and what type of reaction is the reverse reaction in terms of heat. So, um, because heat is going to increase the rate of both reactions, both forward and reverse. But remember that in terms of heat, we have exothermic reactions. They are the ones that release heat, so they don't necessarily need more heat. And then we also have endothermic reactions that absorb heat. So they are the ones that will actually really benefit from heat. So whenever we increase the heat, it favors the endothermic reaction, because remember that endothermic reactions cannot occur if they don't have specific amount of heat. So very important concept to keep in mind. Increasing the temperature does increase the kinetic energy of all molecules. It does increase the rate of both forward and reverse. However, whichever reaction out of forward and reverse is endothermic is going to be increased more, because heat favors endothermic reaction. Exothermic doesn't need heat, so it kind of like doesn't care whether heat is added to the system or not. It's going to need very small amount of energy to happen. So, and that is normally available very easily. So endothermic is going to go faster compared to the other one. Okay, so lastly, let's talk about the pressure, which once again only impacts gases because solids and liquids are not compressible, so they are just not impacted by pressure at all. So remember Boyle's law for gases. So Boyle's law stated that when we increase the pressure, we decrease the volume. So Boyle's law gave us the indirect relationship between pressure and volume. So when you're increasing the pressure, we are decreasing the space between the particles. So when that happens, and let's say we still want to have effective collisions, we're going to have to move towards the side that has less moles. Because remember that if we have okay, that just lost everything that we just did. Sorry. Let me just go to the specific slide that we were working on. So we were on pressure. Okay, so this was your Le Chatelier's principle. We were talking about Boyle's law. Okay, so when we increase the pressure, that is going to decrease the amount of space. So in the limited amount of space, because we want to have effective collisions, which means collisions with enough energy, and with particles that are colliding with each other with a proper orientation, we want to have less moles so that they do still have enough space to collide with each other with a specific amount of energy. So the point is, when you are increasing the pressure, then the reaction shifts towards the side that has less moles. So in this case, for the reaction that we are given as the example, we have 1 plus 3, we have 4 moles on the reactant side, and we have 2 moles in the products. So that means when we increase the pressure, the reaction is going to shift to the right towards the products. So we are going to increase the rate of the forward reaction. Comparatively, when we decrease the pressure, now we are going to have more space. So that means we can have more particles. Because if we have less particles, then they might not have enough collisions. So we want more particles so that they are still constantly colliding and we have more chances of effective collisions. So now they are going to shift towards the side with more moles. So we are increasing the rate of the reverse reaction in this case. So if we are adding a catalyst, this is also something that some people might think is going to impact equilibrium. Remember that catalyst adds the increases the rate of both forward and reverse reaction. So it's going to have no impact on the equilibrium. It can impact the rate of the reaction, but it impacts the rate of both forward and reverse reaction equally. So the equilibrium is not going to shift in a certain direction. Both of the reactions are going to start going faster whenever we whenever we add a catalyst.